How about now? There we go. Dadgummit. Thank you for saying something, Chris. Uh, as I was saying, we're here, we're live, we're ready to go. And I really appreciate you being here today as part of the stream. And just, we're in the middle of busy season. Things are just absolutely crazy right now for a lot of us. And I just thank you. Thank you for being here. Even if all you can do is just listen because you're in the middle of service work, whatever the case may be. Maybe you're doing a repair right now. Maybe you're doing an overhaul. I don't know. But thank you for being here. And thank you for what you do. I really appreciate uh, the sacrifice that you have to put in, that everybody here has to put in order to keep everything we have in our nation actually functioning and safe and alive, right? In so many ways. Even if we're just working on a office building, this is a really big perspective that really helped me rethink a lot of the way that I approach this industry and when I'm servicing a customer, when I'm talking to them. So even if we're just working within an office building and the facilities team we're working with or the tenants within that space, whatever the case may be that we're doing, as difficult as they may be to deal with, realistically, most of those companies, somebody in our community genuinely relies on, whether it be our grandmothers, our mothers, whether it be an important cousin, go down the list, right? Somebody within our community relies on that service. Some of these services may not, like if we don't just take the time to think about it, they may not seem like that big a deal. Or I know for me, a lot of times I wasn't even thinking about who I was servicing. I did not, the tenant of that space really didn't mean anything to me for a lot of years. I was just there to fix some equipment and a machine, and the customer was usually the facilities personnel that I was dealing with. And that was as far as my mindset went. And then one day I began to really kind of just look up and realize, oh, wait, no, these people do this very specific task. I won't even get into details, it's not relevant. But they do this very specific thing. And I have family members who rely on that thing to function well, to help take care of them as part of their daily whatevers, routines. Just keep that in mind. Like, that office building's ability to function as a service and their ability to take care of the other members in my circle and in my community that I care about relies on my ability to get them comfortable enough to focus and comfortable enough to do their job. Whether or not that's right or wrong, it doesn't matter. What I do know is if they're uncomfortable to a point where they can't focus, then my community suffers. So I want them comfortable so that their focus can be what they're doing so that they can take care of the rest of my community. And when I made that shift, it really completely changed the way I thought about service calls, the way I approach things, the way I manage my relationships with the customers themselves. Even if I wasn't working with the tenant directly, most of the time we're not. And that also scaled into like getting into the manufacturing and industrial side of things, realizing that like these, if I want everything that my community needs to work, or if I want the supplies to be on the shelf next time they need to go purchase something, or I know that, hey, this facility manufactures this specific machine, right? One example was a facility I used to service manufactured vacuum pumps, like industrial vacuum pumps for manufacturing processes. Well, when I began to just kind of think beyond this one site, I realized that, well, this is actually, these pumps go into other manufacturing lines, and all of those other lines produce essential goods that my community needs, my family needs on a routine basis. And if those lines begin to have issues and this, like, they can't properly produce and test these pumps without having this chilled water to run through them, like they just don't function, they'll overheat. So if I can't keep this machinery online, then I'm now affecting downstream a whole slew of things that my family and my community relies on. Again, it's this. I don't know. I can't. I don't remember like in a day where I had this epiphany. It was one of those things where probably like over a lunch break or something. I just began to think about this a little more, and then that's when it all just kind of started to click of how much chilled water just completely intersects with so many things that we do. And it really, really helped me get very focused on I'm not here just for people's comfort. I'm not here just to make a piece of machinery turn and rotate. I'm not here just to move heat. Like there's so much of a bigger purpose to what is happening here. And that just lit a fire. Anyway, if you're not into that kind of thing, it's okay. I'm just if that's just some perspective that to this day I still think about, and that's why when I talk about a lot of the things that I do, and I guess I start to get philosophical on some level. This is where it's coming from. So anyway, update on so we had a fun thing with the a train AFD drive last week. Quick update on that. So this was the drive panel that the technician was working on, and when he got into it, he got into the inductor assembly, or inductor assembly. And I did actually forget, by the way, in stream, I realized after the fact, these AFD panels actually have, so they've got a set of inline inductors in the back, and then they run through a capacitor bank. And then that's what feeds over into the actual power assembly, which is where the SCRs, there should be another capacitor bank in here, and then the IGBTs and stuff are. So all that's over here in the power assembly, but they're actually using these, I said they're SCRs over here on the input side. Those are technically on the right side panel. The inductors are back there, which then works in conjunction with the capacitor bank. So anyway, I misspoke last stream, and I'm just trying to correct myself. Either way, these were functioning as a filter. He found that I think one of the SCRs, at least one of them, was testing bad when he got into the power assembly, and I think one of the inductors maybe. I'm a little fuzzy on it. Either way, the job what he had to quote was they're going to replace this power assembly as a whole. So this whole power unit they're going to replace, and I think they're going to do some components on the input side as well. Because if memory serves, I think he had at least one inductor that was not reading correctly. So either way, just a fast, quick update on what he had last week and just kind of following up to give you some feedback on what we're dealing with. It was a fun call. It's something I've thought about doing a lot more. There's just it's really complicated, I guess, in my mind, on trying to do more live stuff. Yeah, there's just a lot of little details that because I want it to be enjoyable for you, right? And I get really sometimes I overthink. Okay, what would you actually enjoy? What's going to waste your time? Like I really, really try to be mindful of these things because I'm not here just for the sake of. Like I want you to. Anyway, I struggle with it. We're going to figure out a way to do more live stuff eventually because I think of it like talk radio. That's an example I used last week when I was discussing this. Talk radio, where you could call into the radio and have a conversation with the host live on air and stuff. That was a whole thing, and I think there is a way to replicate that. I do think of it that way, having like a talk radio show that you could call into, get on air, have a quick discussion, jump off, move on to the next thing, kind of environment. So I don't know. It's something I'm pondering on. I'd love your feedback on that. Don't even know if that's something you would truly want to do, you'd feel comfortable doing. Like, would you feel comfortable calling in and having a live conversation to whereas instead of me just reading off an answer and spouting off to you and just kind of pontificating ultimately, actually just getting to talk through it in real time kind of a scenario. I don't know. It's a lot to consider. That being said, fun thing I want to start showing more of the community. I want to start giving I want to get everybody more involved, I guess is how I'm thinking about it. So like these here, Mechanical Concepts, these folks are out of Colorado. Absolutely wonderful people. They've been great friends of mine for a long time. They've been huge supporters of the community here, and contributors at that. And so, wearing their shirt today, this is a Air Performance hat. So this is the team I used to work with out of specifically San Antonio, is where I got this one. And so what I want to do, I want to, for everybody in the community, I'd love to start broad. Like I have a collection already of some shirts and hats and stuff, but I really want to expand it. And what I'd like to do is just kind of make that, I want to show all of us together, right? And I want to show how we're just kind of unified in our own way, whether that be through wearing hats or wearing t-shirts. Like I'd really like to do that. And so, if you want to send me, if you want like your team and your company represented, and you get to see that, hey, we're a part of this community, I'd love to wear your stuff. So I did post in the comments. So P.O. Box 3112, Fredericksburg, Texas. That is the where you can not email, you can mail shirts or any hats, any kind of stuff like that. I'm cool with stickers too. Never really got into the sticker thing, but I'm more than happy to receive those if you have something like that. But feel free. Like I'd love if you would like to be represented here on stream or just in any kind of content. You see how much I wear these guys' shirt. You've seen me wear. There's a couple other companies that I wear as well, and just I don't know. This just sounds fun to me. I really want to get into it. I'd love to get far more people involved and just make this really, really cool collection of everybody that's gotten involved here. In terms of shirt size, I am a 2XL. All right, so I'm a 6'5", about 230 weight wise. So not a small guy. So I'm a 2XL on the shirt. That's what this is currently. Fits me perfect. And then my favorite hats are Richardson's. Now I'm not that particular, so I'm happy to take whatever hat brand you have. But if you do have Richardson, I appreciate you. I don't know. There's just something about their hats. I don't have a specific like model of theirs necessarily. I think it's just more of the like this is one of my like really nice fits. This is the 112, the model 112. Again, I don't know Richardson's on a level of like telling all that, but I just know that Richardson's have been the hats that have held up the best for me, and I've just really, really enjoyed them. If you've got other brands of hats, if that's even something you pay attention to, that you're into, again, I love hats. Hats are a huge part of my life at this point. Like I've always had them. Anyway, getting off in the weeds here. So yeah. P.O. Box in the comments. Send me an email. Let me know if you're going to send something out. That way I know to be looking for it. And I would love, 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 love to add you to that collection and then get to rep your stuff here on stream or in videos or just in general on whatever I'm doing. It's really got me thinking about, I could wear the nice shirts and stuff with the collar and they look great. They're comfortable. Like I do really enjoy those. I think they're McGlellan shirts or however you pronounce that. But to be honest, I'd much rather wear something that means something to all of us, and that is like ourselves and each other and kind of representing here. Anyway, I will move on. I've had my spiel. Thank you for listening. Thank you for your patience. Let's go. All right, so we do have one question. What is economizer and what is site sensor? Okay, on that economizer question, I assume I did a couple of clarifications. Are we discussing a refrigerant economizer or a water side economizer? Yeah, I appreciate you. There's Matt right there. How you doing, bud? Or yeah, just really appreciate you guys. Yeah, water side or refrigerant side economizer. I can cover both ultimately, like in a structured way. I just give me a little more information on the economizer. I do have a question we're going to dive into first, and I'll give you some time to just, if you give me a little more detail, I could give you a more direct answer with that. Let's get into this one. Please also touch on the best approach to test electronic sensors for defects. So let's start off with, let's grab some sensors and I'll kind of talk through them. This. This. Okay. Ooh, you know what? Hang on. We'll do this. Okay. We got some toys. Refrigerant type on the economizer. Got it. Do you have a model at all on that economizer? Not that it's overly important. Again, just it helps me kind of understand which machine you're dealing with. That we do it in different ways. And do you know if it's a flash tank or a braze plate? So do you see a braze plate, or is it a different? If it doesn't look like a braze plate, it's going to be a flash tank. Okay, let me get myself organized here and we'll dive into this. So in terms of electronic sensors for defects, so basically I take that question as just a failed sensor, right? Is a sensor failed, and what kind of sensor are we discussing? So we could be describing a thermistor of some kind, which is what these two are. Now, two very different thermistors. All right, so this is what we'd use on like a supply air temp sensor. Okay, that could be one use of it. You could also use this for a leaving water, entering water sensor for a BAS system. It's going to tie into a controller. So there's one example. This is a actual immersion wet well style sensor where this is going to sit in the refrigerant stream and then give us a temperature feedback that we can then make something useful out of. All right, so there's thermistors. We also have a like rheostats or varistors. We do use these quite commonly throughout the industry in various ways. This particular one came off of a YK PRV position sensor. Then we have transducers, which are usually just a basic 3-wire setup. There are more, call them fancy versions of transducers that have a much higher response rate and such. We can get into those details, but this is just a basic transducer. I think this is a Danfoss. No, Dunnan sensing. Anyway. And some people would look at this as a sensor, I guess. It's just a pressure switch, basically. So it would function the same as a low pressure, high pressure, stuff like that. So that's what we'll just talk. So in terms of like, how am I going to approach and like, is this good or bad? Well, let's start off with the thermistors and we'll go from there. So on the thermistors, we'll just start with this one here. There's a couple of ways we can go about this. One way is if we have a thermometer, which I don't have one sitting close by, but here, we'll use this. So let's say I had, I was using this as a thermometer, and whether it was inserted into the airstream or the water stream, maybe this was, let's just say we're reading leaving water temperature with the automation system with this sensor. Okay, so this is sitting into a well in the pipe, we're getting water temp. So let's say I had a temperature probe that I was also able to insert into the pipe and monitor water temp. That being said, if I'm confident that this probe is accurate and calibrated, and I've done so recently, then I'm just going to compare these two, and I want them to be within 2 degrees. Okay, so I want this sensor to read within 2 degrees of my probe. That is the industry standard as a whole. And as long as I'm within 2 degrees, then I would consider this thermistor calibrated, close enough, right? And I prefer to do this close to the operating temperature that I expect this to function at. So if this is functioning at a, like if we're, let's see, there can be cases where, let's say we pull this out of a chilled water stream. So this was sitting in 40 something degree water. We remove it to test it. It's sitting out in a 80 degree ambient. Okay, well, it's possible that when you go to test this, if it's just sitting out in that 80 degrees, that this might read close to accurate or within that 2 degree span at 80 degrees. But by the time that we actually get down close to our operating temperatures, which was in the 40s, that's when all of a sudden this is reading 4 or 5 degrees out, which can be enough to really screw up a control sequence. So it's important that if I can, it's not always possible, but if I can, I want to read this close to the operating conditions I expect this sensor to function at. That is true for a lot of these, right? Now, some of these it is less impactful, but especially with like my thermistors, I want them to be close to operating. So that's one method. We're going to use a calibrated thermometer and we're going to test that way. Another method would be to, if we have a temperature chart. So I could probably, if you want to look that up, I'm not going to take the time here live, but that is the part number for this Honeywell thermistor. Okay, so you can look this up and we should be able to get a temperature chart based on that. A lot of the manufacturer OEM manuals will give you a temperature conversion chart for the thermistors they use. There's different types of thermistors, so you have to keep that in mind. So depending on the type that you have will depend on how that thermistor is going to scale and what readings we expect to get from it. Now I'm going to switch over to ohms. We're going to go, we'll go 20K. I guess that's 200K either way. So we're going to go ohms, and I want to see what reading do I get. So that would be 22,000 ohms. All right, so then I would take that ohm reading. With this, in this case, I need to know, again, what my actual reading is I'm comparing it to. So we still kind of run into a similar issue here where if we're doing this for calibration testing, we still have to have a temperature we're gonna test this to. So there are cases where you may have a machine that, especially if you're working on an older machine, it may not tell you the leaving water temperature on the control panel because you may not have an interface. You're not going to have too many of those nowadays because most machines are going to have some kind of readout. But in the event that you did come across a machine that you did not have an interface to interact with, or maybe you don't know how to use the interfaces there. Either way, we still have to have a temperature to compare to that we know is accurate. And then we're going to take this ohm reading, use that chart, and then that ohm reading with the chart will get us the comparison. We're still looking for that 2 degrees. It's also the case that if you're questioning, is it the thermistor that's having an issue or is it the control module? There's going to be cases where the control module is actually what has gone bad and it's not reading the temperatures correctly. Now, normally in that case, you're going to see many temperature sensors all of a sudden just don't look right. And it's because the input terminals on that module for those sensors, where you'll have multiple sensors coming into the same input, and all of a sudden several sensors just don't look right on the readings, that's an immediate giveaway. May not be the sensors. So if you have that chart, you can actually take a resistance reading and compare it and say, okay, is my sensor actually giving me a bad reading, or is my module not reading it correctly? Is it not monitoring the ohms correctly? Now, I will tell you, another way to check this is actually voltage drop. So I'm not able to simulate it here, but let's just say, flip this around. So we have our inputs right here on these purple. So I would switch over to VDC. And in this case, I'd go to 200 VDC or 20 VDC. This would be a 24 volt system. We should be sending out 5 volts DC on our temperature. Most of the time, 24 volt controller, your thermistors are going to have a 5 volt DC sent through them. So we could then read across those terminals for where the two thermistor wires connect and read our voltage drop. Okay, so that's how the controller is actually monitoring the resistance. So as the resistance fluctuates, our voltage drop across the thermistor fluctuates with it. We convert that into a temperature. So if you don't want it, if you have a voltage drop chart, usually they're going to be resistance charts. You may even have a voltage drop chart. If you do, then you can just take voltage drop at the controller and get what is essentially the same reading. Now again, if the voltage drop is correct, that doesn't mean like the module could still be reading incorrectly. So these are just ways that we can try to figure out, is it a sensor? Is it the module? And if you're ever unsure, I will say that it is far cheaper to do these thermistors than it is to do this module. Far cheaper, faster, easier, everything possible. So if you find yourself in a spot where you're genuinely uncertain, which is the better path, I default to, okay, well, you know what? I can't hard guarantee one or the other for whatever reason. Doesn't matter why. We're going to start with the sensor. If we still have issues after the sensor, then we will just have to move on to the modules, the only other problem at play. And then we'll go from there. So that is a way that we can try to isolate. Again, we need those charts in order to be able to read that. Using the voltage drop and resistance, which we can grab this here. I do want to show you. I just find it kind of fun. Grab this, and then I'm going to grab the tip of this. And as my hand heats this up, yeah, see, we see the temperature, the resistance begins to fall as heat increases. Now, I used to have like type 1, type 2, type 3, like being able to determine if the temperature increases, resistance decreases, and vice versa. Like this is where, because some of them, as it heats up, resistance will increase. And this one, as it heats up, resistance is decreasing, which I think this one is a type 2 style. Either way, I don't have all that 2 memory like I used to. But you got to see, like as I hold the thermistor, temperature is increasing. Something you have to be very careful of is if you're going to, say you don't have a way to read the water temperature without the well that this is already sitting in. So you want to pull this one out, put your temperature in, and then use that as your calibration comparison. I don't really recommend that because unless you've got extremely stable conditions, because the moment you, like if there's any kind of fluctuation at all, it may not be that the sensor is the issue, you just saw the fluctuation, but then you might condemn the sensor incorrectly. Anyway, and we'll take a quick look at this. So this is a refrigerant sensor that actually sits in stream and gives us our refrigerant temperature, which we then convert to a pressure on this. So this came off of a RTAA specifically. Let's just see what we read. Yeah. So we got 10,000 ohms, 10,500 ohms right there. And then I wonder what happens on this one if I just grab it. Again, I'm just doing this for fun. The sensor was replaced because it was bad. It was not reading accurately. Yeah, so as it heats up, it looks like this one's gonna start to fall. I want to point out the difference you're seeing. So both of these are at ambient in this room, which is lower 70s right now. But this one is reading 20 something thousand, like 22,000 when I first pulled it out before I grabbed it with my hand, and this one's reading 10,000. Okay, just to kind of show you, these sensors run on two different scales, and that's where having that temperature relationship chart to be able to graph like that specific sensor, which the OEMs do actually provide us quite often. A lot of them will give you a temperature chart for their temp sensors. You just have to look through you have to have the manual, but then look through the manual enough to get it, which commonly their basic manuals will contain that. Okay, let's move on to a transducer. So transducers can be kind of a pain, and that's because like at this end where the plug is, it's really difficult even if you have a set of the needle probes, right? So this is the standard probe. Even if you have a set of little needle ones, they can be a pain to read at the temperature at the transducer itself directly. But there's a couple of ways that I try to do this. So one, I usually try to make sure that a transducer is within 5 psi. So if this is mounted on the refrigerant system on this suction line, let's just say this is our suction transducer, I'm going to try to find a different point on the suction line that I can connect to that is relatively close to this one. And again, I'd rather be close to operating pressure. So with the system off on the suction would be higher. We could read closer to accurate at those higher pressures, but the moment we start the machine up and we get down close to operating pressure, that's when we start to see that we're on calibration in operation. So if I can, I want to get as close to this sensor as I can in the circuit, because there are different pressure drops that happen, and I don't want the pressure drop to influence my calibration check. That's really, really important. So then yeah, I want if I trust that I have a calibrated pressure gauge of whatever kind, whether it be a digital probe, which is what most of us are using nowadays. That's what I use. So I like the Testos specifically. I've just used them for a long time. Field Piece does have good probes as well. And I know Navic has come out with their own line. So I'm going to try to connect as close as I can, and then I'm going to compare those pressures, and I want to be within about 5 psi plus or minus between the two, between the one that I consider calibrated and this one. If I'm outside of that, I am condemning this transducer, just like I would with a thermistor. So that's one method of doing this. Now, if we have it to where we're just not getting a reading at all, well, it's important. These transducers have a continuous input voltage. All right, so if you're familiar with actuators, like a proportional actuator that you give it a 0 to 10 or a 4 to 20 milliamp signal and it adjusts, well, those have a 3-wire where one of the wires is a input power feed. That is also true for transducers, which this one is a 5 VDC transducer. That means that we are going to provide a continuous 5 volts DC. And so of our 3 terminals in here, we would have our, see if we can get it where you can see it. We'd have our 5 volt DC VDC input. We'd have we're just going to call this bottom one down here ground. Okay, that's our common. That'd be a better way to say that. So we have our 5 volt DC input, we have common, and then we have our reference or our feedback going back to the controller, which for this particular transducer, I would expect it to be a 0 to 5 volt feedback. So we're going to send, depending on our pressure. So, for example, in a very hyper simplistic version, if I'm 0 to 5 volt feedback and I'm a 0 psi to 100 psi transducer, then at 50 psi, I expect a 2.5 VDC feedback out of this going back to my control module right here. Okay, this is just an example. Don't get too hung up on the specifics here. Okay, that's what I'm looking for. So if I'm having trouble with my transducer, I do want to verify, am I feeding it correct voltage in the first place? Because if it's not getting fed correct voltage, it's not going to report correctly, period. So that comes back to the controller. You're going to have a 3-wire termination for this transducer. So there'll be 3 wires. Now they may not all be side by side. Some cases they will be, some they won't. So if they are, so just be literally on the control module 1, 2, 3. Okay, there's my 3 transducer wires leaving. In other cases, you may have your reference wire, and over here you may have a common power feed out that's feeding several sensors, and you may have a common wire or a single common that's multiple sensors are sharing as a common, right? You may have some of that kind of thing, but you'll still have a dedicated reference over here by itself, but it may be sitting next to several other sensors with dedicated reference inputs. The point being, you'll just have to look at the schematic and see where does that transducer tie in, and then go read between what's supposed to be power out to the transducer. So in this case, it'd be 5 VDC, and that transducer is common. I want to read between those two things, and I want to see 5 VDC proper. And if I don't, then why is my controller not outputting correctly? So then we can shift, is it a transducer issue or is it a control module issue? These transducers will have pressure to voltage charts, to where if we're at whatever pressure you have, it should be this voltage output coming back. So if I have a calibrated gauge, and again, the only reason this really matters is if we're questioning transducer or module, or if we have a control panel where we can't see this transducer pressure. The controller's monitoring it, but it's not giving that pressure to us on the display. There will be times where this is going to be true. So we're trying to sort out, is it actually the transducer or is it my module? And I want to be certain as to which is the problem, because I can see that it shows to be a bad calibration, right? So it shows that my calibrated gauge to this transducer are not reading within 5 psi of each other. They're reading outside of that. Maybe it's 10 psi. Okay, no bueno, not going to good. So that being said, if I can verify that I have 5 volts proper feeding the transducer, so I know I'm feeding it the correct power, now I want to verify, is it giving the correct reference back? And I don't want to just assume it's the transducer. Now these transducers, okay, unlike a temperature sensor where it is usually cheaper and easier to just, if a thermistor goes, just call the thermistor. That's not always true for a transducer, especially as we get into larger machines. It may not be cheap or efficient to do that transducer over the module. Now the part itself may be cheaper, yes, but the process to replace that part, it may not be. It could be, it may not be. So I really want to do my best to verify, do I think it's actually the transducer or do I think it's the module? And I want to sort that out as soon as I can. So this is how you can verify that, with just checking the actual references. And then if you can, get a voltage chart, right? Because one of the ways I've always done this is I will look at the actual model number on the transducer, which, not that you're going to be able to see it, but you can just see that it is labeled on here. So what I will do is I will research. Like this one I would pull up. It would be an HVP 0667S01-S17. All right, that's what I'm going to search. And I'm going to pull that up and see what kind of documentation can I get on this transducer. It's very common. You can find it. Very, very common. Like for me, it's uncommon not to find that chart somewhere. So that being said, once I have that, I can then reference, okay, it says I'm at this PSI. Per the OEM, I should be outputting X voltage. Am I or am I not? If I am, then I'm going to start paying attention to why is my module not reading it correctly. If I'm not, then I can for sure with confidence say it is without a doubt that transducer. Most of the time it will be the transducer in my experience. The vast majority of the time. So especially if this transducer is easy to replace, which is going to be particular, like if it has isolation. Okay, so if we have a service valve this is mounted to and we can easily isolate the refrigerant circuit and just swap it out. Or if we can do a pump down potentially, or if we're just talking about a small refrigerant circuit. Okay, that's going to make this easy to service. In that case, I'm probably not going to take the time to go through all the extra steps because I can just, this is small enough, easy enough, and cheap enough. I'm just going to recommend let's replace it and let's move on, because majority of the time this will be your problem. But there are going to be scenarios where it's not easy to replace. It requires a major service just for the one sensor. And it could be the module. And we really need a way to separate the two and verify one or the other. So that's how I'd go about that, is getting that chart, comparing that, seeing which one of these is reading inaccurately. Because if this is outputting what the OEM says it's supposed to, but I'm still showing the wrong pressure here or something to that effect, I know I've got an issue. Okay. So we've talked about thermistors, we talked about transducer. Let's just talk about this rheostat real quick. For these, so this is just a variable resistor in the end. And I'll show you here. It should be the two outer prongs, if memory serves. Give me 1 second. And we rotate this. We should, yeah, there it is. So you'll see that it just, as this rotates, we have our resistance fluctuate. And then we can convert that into a position. All right, just whatever kind of position we need to, IGV position, actuator, damper position, yada, 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 valve position. So, because you'll also see these on Belimo's. Belimo has a attachment module that is a rheostat position feedback that your automation system can use to monitor its position. Instead of it being internal into the actuator, it can actually do that as an external device. So I would encourage you to just kind of look into that. But so you're going to see these in various applications. Basically, the main thing I'm looking for here is I'm going to check my resistance, and I'm going to just see, do I see fluctuation? Okay. There's not a whole lot more we can do with something like this. There's really not. Can we do a calibration? Yes. That's really the best path that we have if the system allows for that to happen. If we have the ability to, like on this YK, for example, these will fail. They do go bad. And they will drift to a point where you do not get the proper range on the resistance. It's kind of got some, like, almost like a dead zone, if you will. In that particular case, it is important to try to run the machine through a calibration. And you can do that in the control panel. Those BELIMOs, so typically what an automation does is when it goes to calibrate the valve, some controls or some automations, like once it registers as fully open, for example, it will save that resistance value that is getting fed back as the fully open position, and then it'll do vice versa on the close. It'll move it fully closed. Whatever that resistance value is, it will save, and then that means everything in between is in the proportional step that that position. Okay, so the halfway between those two resistances in distance, we would expect to be 50%. So it's able to run all those calculations. So that's if the system is doing that. If it is not, and this just begins to read incorrectly, even if you put, so here's the thing, even if you put a new one in, you still have to calibrate. So we need a way to calibrate either way we go with this. I don't know that you're going to truly get around that ultimately. So anyway, that's a rheostat. There's not a whole lot to verify here, right? It's just, do we have resistance at all? You probably aren't going to get a chart or anything else for these. So then it's just a matter of, okay, do we have a reading? Does that reading fluctuate? Okay, it's not just a static single resistance and it's not moving at all. Okay, that would be a failure. So we need to make sure that we are changing resistance, and from there it's just a matter of calibration. Then with just basic switches like this, I mean, this is just a basic switch. We're either open or we're closed. There's not a whole lot of in between. So what's this one should be, I'm actually trying to remember now. Let me get myself out of the circuit. Yeah, this one is closed, which this is just a thrust bearing sensor on a Y case centrifugal. Again, it's not really that important, but this would be any kind of switch, okay, whether it be a high pressure, low pressure, thrust bearing, oil pressure, like just any kind of safety switch we have like this that is specifically pressure related. It's open or closed, and then it's just a matter of, what is the trigger point. So some of these will actually say on them, which this one does not, which is okay. A lot of them you're going to run into, they'll have that on them. These are going to troubleshoot just like an RTU pressure switch would. Okay, so if you can do that on a split system or an RTU, it's the exact same troubleshoot process. There's nothing unique or special, even if this is used in a chiller application. Some of them will have a push button reset if they trip. Others won't, like this one. This one does not. So it is as simple as just, it's either open or closed, and then it's a matter of, okay, what is the trigger point or the trip point or the set point, whatever you want to call it, that causes this to open or close, and in like kind. So keep in mind that they may not always be normally open. Some of these will be normally closed, and then it is seeing the excess pressure that causes them to open, and that becomes the failed circuit. So, or they may not be normally closed. Yeah. Some of these won't be normally closed. They will be normally open, and seeing pressure causes the circuit to close. Anyway, that's all it is. It's just a switch. Beyond that, that's in terms of the core sensors that we're going to run into the most. That's what I expect. Now, in a case like, let's talk about Train for a second. With their, they run a COM bus on all of their sensors. It's just even their thermistors, their transducers, all of their stuff has a communication bus that runs throughout the machine that everything plugs into, and you have to bind, unbind, go through that whole process. In that case, what I am paying attention to is I'm going back to actually just using another sensor for verification. And that's my main method of calibration. And the whole concept of, is the Um, is the actual control module itself the problem? Well, at that point, it's more of a data bus issue and a firmware issue than a hardware issue for those sensors, because they all do plug in. Now, not everything plugs in. There are some stuff like the external flow switch that would be field installed that comes into a little I/O module. So there are some sensors that will do that, but a lot of the sensors on that machine will be just strictly plug in via the communication bus that they use. So with that case, we are limited to just having a calibrated sensor or gauge, compare those two for calibration, and then move on from there. There's not a whole lot more to that process, and you're not going to trace it back to the modules and stuff like I'd already described. Anyway, moving on. How you doing, Jason? Good to see you, bud. I see everybody there. I do see a couple of questions. It looks like Jason is responding to the dry bulb. Let me read that in just a second. I'm about to get to the economizer question. I will throw it out there one more time. I put it in the top of the chat feed. But if you'd like your team represented here in the academy on stream or just anywhere at all, whether it be via hat, via shirt, either way, feel free to send those over to me. The best place to do that is my P.O. Box, which is P.O. Box 3112, Fredericksburg, Texas, 78624. From there, like I'm wanting to really get more folks involved, and I want to expand the collection or the library and represent more of everybody that's gotten involved and is a part of this community. So it means a lot to me. I want to represent if you want to be represented. And whether, like I said, whether it be hat, whether it be shirt, I am a 2XL on the shirt. So if you do send anything, I'd like to be able to wear it. That's my goal, is to actually wear it. So I just requesting the appropriate size, and then send me an email to just let me know that it's on its way. Like I said, it doesn't have to be a shirt. It could be just a hat. Either way you go with it, I'd love to get some stuff from you and just get your team represented here. And that's true across the board. I don't care where you're coming from. I don't care the nation. At this point, we are fully international. There's very small pockets of the world that we don't currently function in, and that's like one of them is the African rainforest. One of the few places where we don't show to have active folks in the community here. So that being said, please feel free to get it over. All right. Let me read one of the questions. Please teach me about dry bulb temperatures, because this time. Okay, yeah, we'll circle back to that's going to be a great. Yeah, we'll circle back to the dry bulb question here in just a minute. And I'm going to get the economizer question loaded up here. All right. Okay. There's a lot to discuss with this. I do explain these things in great detail in my chiller certification course at chilleracademy.com. I'm just pointing that out because I will need to just keep it a little more abbreviated in what we described today. But if you do want to go deeper and get a complete kind of broken down picture of this, that is the best place to do that. That being said, what is economizer and what is site sensor? Explain like how economizer works in chiller and what its role in chiller and cause of failure of economizer. All right, so do I have a good example? I don't. That's okay. So there's two primary types of economizers, and we're going to be covering refrigerant side economizers specifically. So we have brace plate. I'm going to say BP, and then we have flash tank. I'm just going to say flash. So brace plate, flash tank. Brace plate are very much what they sound like. So we're actually we'll have a brace plate with 4 ports. What ends up happening is we have the liquid line comes down and feeds into the top of the brace plate here. This comes down out of the condenser, and we feed out of the bottom of the brace plate going to the evaporator. All right, so it's going to evap and condenser, flowing this way. Now, one of the things that happens in this process is we have a T. It will come off on a T, and we will feed via a metering valve right here into this other side bottom port of our economizer. A lot of modern machines are using EXVs here, but you could still run into some with a TXV. And then what happens is we have our flash gas, medium pressure flash, go back to the compressor econo. Okay. So to summarize this, basically what's happening, we're bringing, say, 8 to 10 degrees subcooled liquid refrigerant out of the condenser, feeding it into the economizer. We have a T taking a little bit of that same liquid refrigerant, but processing it through the other circuit of the same economizer, heat exchanger, and we're not, see, here's the thing to keep in mind. We're not taking this down to low pressure, okay? We are flashing this gas through this metering device to a medium pressure because our goal is to increase subcooling on our liquid line before it gets to the evaporator. Something you can dive into later is refrigerant effectiveness, okay? So we have our pH or PE chart where we have our pressure enthalpy and our refrigeration curve. So this will be pressure, this will be our enthalpy. So from here we have our refrigeration cycle, yada yada. Both of these economizers are utilizing this effectiveness chart, and our goal is to better optimize the effectiveness of the refrigerant that enters the evaporator. We do that by ultimately adding a line right here. Okay, there's a line that comes across at a midpoint. Is highly simplified, but to get the concept across, that increases the effectiveness, basically improves the efficiency of the system for the refrigerant we're sending to the evaporator. That's what we're doing. So we want, say, 10 here. We might be 20 something degrees Fahrenheit leaving here of subcooling. Now to do that, let's just say, we had it was 10 degrees subcooled, and we had a liquid line that was 100 degrees. Okay? So our liquid line is 100 degrees Fahrenheit coming in. We are 10 degrees subcooled. Then our objective, if we want to get to 20 degrees of subcooling, is to make this 90 degrees leaving. Keep in mind, this heat exchanger doesn't need to be down at 45 degrees of saturation on our economizer circuit in order to achieve this. We just need to be we just need to be a bit lower than that 90 degrees, basically. So most of these heat exchangers are about 10 degrees of approach, without getting too off into the weeds in terminology. Basically, if we had a refrigerant saturation on the economizer circuit of 80 degrees, let's say 70 to 80 degrees, we can achieve this drop from 100 degree liquid line to a 90 degree liquid line, increasing our subcooling by 10 degrees by processing through this. That is what we did. So this other circuit of the economizer is creating a medium pressure. So this would be high pressure. We're still high pressure coming out the other side. Okay, so over here we are a high pressure circuit because we haven't gotten to our metering device for the evaporator yet. That comes further over. But we are a medium pressure going through the other circuit of the braze plate economizer. And then the evaporator would be your low pressure. Now, in terms of what this medium pressure is, it's going to vary based on your conditions, okay? So obviously, the higher the head pressure you run, the more likely you're going to run a higher economizer pressure. But it's still going to be in between. It's not going to be your full-blown head pressure, your high pressure side. It's definitely not going to be anywhere near your low pressure side. So anyway, that gas gets sent to a midpoint on the compressor. I've got some really good examples of this coming in. But yeah, I don't want to muddy the waters. Okay. Essentially, let's just assume, whether it be so if we had a centrifugal, we'll just do this. We have two impellers, okay, on the same shaft. So this is stage 1, stage 2. Right here in the middle, this is your interstage pressure. So this economizer gas, as it gets sent through, gets flashed, and it comes in as a interstage. I do see your messages there, Jason. Do appreciate that, Bubba. Let's pull some of these up just so you can kind of see what I'm discussing. So this would be an example of like how this might look. So this is the metering device for the evaporator right here, coming out of the line. This is the liquid line coming from the condenser. Okay, so we see this coming down, up, up, up into this braze plate. Now it is insulated. And then we also have a separate line. Now this is a water-cooled machine. We have a separate line pulling liquid off the bottom of the condenser, feeding up into this metering device, which we can see the EXV head right there. It is insulated, but there's the cable, there's the sight glass. So that's going to feed. We go to a medium pressure here. We feed up. We are subcooling the liquid line, and then this feeds back up to the economizer port, which you can see. We zoom in. Right there, this is a turbo core, by the way. So this is a Daikin WMC. Right there is our economizer input, which feeds right here in between those two impellers. So that particular line has two impellers in it. If this was a screw machine, so we have our screws. This can also work for a scroll. There are scrolls that have interstage inputs in them. You will see them in VRF machines. They have a refrigerant side brace plate, just like this, economizer inside of a VRF. Anyway, Your interstage point is right in this zone. Okay, so the flash gas or the economizer gas comes back right in this zone right here, back into the compressor. All right. In terms of, so part of the question was failure. What does failure look like? All right. Really important piece to this. Well, failure in this case would be more commonly we overfeed on the economizer metering valve. That is the most common failure in this particular setup. And by overfeeding, we end up pushing liquid refrigerant. We're not fully flashing. We end up having liquid refrigerant come back into our compressor. And that just absolutely destroys and tears stuff up. So it's flooding, right? It's no different than flooding. If we were flooding refrigerant back on the suction line, it's the same process, except we're sending it right into the middle of the compressor. So, like in some of these cases, we use this screw as an example. You have the motor section that the refrigerant, if it's usually suction cooled in these cases, the refrigerant passes through the motor and then gets to the impellers. And that motor will actually help mitigate a little bit of flooding, a little bit, right? Not a whole lot, but a little bit. So you could have a fairly low superheat wet suction coming back into the compressor, and that motor is going to end up vaporizing it as it passes through the motor assembly before it gets to the screws. That economizer port doesn't go through the motor section. It goes straight into the screws. So if that economizer overfeeds and floods back, it's going straight into your compressor. Same basic concept with the centrifugal side. So centrifugal screw compressor. Again, scrolls also have this, but right now they're just less common. I do fully expect to see this far more common on scrolls as we move forward. Anyway, that's the process here. So that could fail. It could also fail the opposite way, to where this is no longer feeding correctly. So a lot of these will monitor superheat, or they may be controlling via just pressure. So instead of monitoring like superheat, leaving this, because they may be trying to just control a specific pressure on the economizer pressure leaving line, right? So there's a few ways that it can be done in this particular version. Now, it'll be slightly different on a flash tank, but superheat is the most common method I have seen, that we're monitoring suction or your interstage gas pressure, temperature leaving the economizer, and then we're going to control via regular superheat control from there. So if we had a 80-degree saturation on the economizer circuit, and we want a 10-degree superheat, then we would expect our return gas to be 90 degrees. Yeah. So this could fail closed, to where it's underfeeding, which at that point you're going to have reduced capacity in your evaporator. You're going to run less efficiently. It's going to struggle to keep up correctly because we're not getting our extra subcooling here. And so because this subcooling is not happening, we are not able to maintain the evaporator the way it's designed to. And so that's going to cause some capacity issues. Keep in mind, these economizers usually are not engaged or actively trying to process in light load conditions. So you usually will need to get above a certain load, a minimum load value, which could be motor current, whatever the case, it's very commonly motor current. You have to get above a certain value before these will be allowed to engage and start actively affecting the refrigerant circuit. So instead of this is a way of staging up the circuit's capacity. So instead of actually having the compressor ramp up more, engage the economizer, you will start to get more cooling without actually having adjusted the compressor's capacity. Okay. Yeah, short of a leak from there or just one of the sensors, that's about what I would expect. in terms of this economizer specifically failing. Let's dive into a flash tank. So with a flash tank, we have a literal tank, and we're going to feed we're going to have our refrigerant come in. It's going to hit a metering device. So we are high pressure on this side, flowing down. Then we will feed into our flash tank. Now, because we are flashing off here, we will have a vapor liquid mixture. So the vapor will collect at the top, the liquid will fall to the bottom. From there, we will have the another port that pulls from here and goes back to the evaporator with another metering device. So we are still medium pressure here. So this is still medium pressure. This is going to the evap. And then over here, we would have our low pressure, high pressure from the condenser. But then we have that same basic economizer flash gas line, or we call it flash gas here, hence flash tank, but economizer vapor line going back to the compressor economizer port. So economizer, compressor port, compressor economizer. Either way, that'll go back to these same ports here and pull all that flash vapor off, while the liquid that fell is getting sent to a metering device to then flash from medium pressure all the way down to the low pressure. Going from medium pressure to low pressure to then process through the evaporator. Again, we're just utilizing a PE chart. That's all we're doing. We're maximizing the refrigerant effectiveness via this chart. Okay. Most everything else kind of stays the same here. It's very common to have a refrigerant level sensor here. So it's very, very common that these will run level sensors on this part of the system. There are some machines that do not actually control level in this. I'll give an example. A York YVAA does not actually control the liquid level in the flash tank on the later, or I guess on any of their models. So this is if their YVAA has a flash tank. Some of them will have a braze plate, especially the newer ones. The Mod Bs will have a braze plate, and you'll have a flash tank on most of your Mod As. So with a flash tank design, we have a condenser drain valve that is controlling via subcooling. So we have a subcooling set point. I think it's of like 12 degrees is the default. And so as we see subcooling get above that, we flow from the condenser to the flash tank. And the level in the flash tank is not controlled like it would be if you were working on a YCIV. All right, so a different version of an air-cooled York screw. Those a YCIV actually control via liquid level sensor, and they're looking for a set point of like around 35% or so. Whereas a YVAA is controlling for subcooling in the condenser, and then they're just flowing through. But everything else in the process stays the same. What changes is just how we're controlling each of the valves and what they're doing. On a YVAA, this is a fixed orifice, just in line. So there is a metering device there if you just have to be aware that it exists, because it's not obvious just looking at it. Whereas on a YCIV, this would be an actual EXV and an EXV on both of these. Some machines will control the economizer via a valve. For a lot of times, what they'll actually, I say some machines, most of machines will control this via a valve here on the flash tank, um, vapor leaving the economizer. So it gets back to the same concept. Low load situation. We'll have this valve up here closed. We may still be flowing through the economizer, but we're not actively processing the flash gas. All right. So we're not operating at the same medium pressure state. And then we want to engage the economizer and use it to help increase capacity. So we then open the valve accordingly, and we start using that medium pressure and getting more effectiveness, more capacity out of the refrigerant. Let's see. In terms of failures, the liquid level not being controlled correctly is one major failure. This results in just flooding back. So you will get liquid refrigerant back to your compressor just the same. EXV failure, sensor failure. These aren't monitoring like superheat and stuff like the braze plate does. So if these are monitoring at all, it is usually a liquid level sensor. Some of them will have a level safety switch so that if for some reason the level got too high in here, it triggers a safety switch, it's just a float switch, like a condensate drain. Okay, when a condensate drain fills up too much, switch triggers because it literally just got to float, and that shuts the equipment off so that we don't overflow the condensate. Same basic concept, except we're just not allowing liquid refrigerant to fill up too much so that we don't send it back to the compressor. Not all flash tanks will have that, but some will. And that can happen when that level sensor fails and it's not registering that it's really high level. I would say, yeah, those are the primary failures. The metering device is failing or that level sensor having an issue would be what I have seen to be the most common. Let's see. Getting back to the original question. Works, chiller. What is the role in chiller cause? Yeah, I think that pretty well summarizes that. Again, this is all refrigerant side economizer. All right, there are also water side economizers, a completely different subject, but just aware that they exist. If you want to look that up, again, I go into this in much better detail and show this in my online certification course. So feel free to utilize that and to get a more complete breakdown of this whole process and get more examples and what it all looks like beyond just me doing some doodling here. All right. It's a good question. Okay. How you doing, Nick? Cover some carrier 19XR stuff like wall cycle flash, float chamber, etc. Yeah, we can get into some of that. I do have another question we're going to get into first. So first, let me kind of catch up on this. So please. Let's just get this question loaded up and then we'll go from there. So the YVA economizer line tends to crack when it's going back to the compressor, and yeah, so this comes back to vibration. Especially the earlier models, they had many issues with vibration fracturing on the lines. So I would also want to make sure that you're not having an IGBT issue. So one thing to keep in mind with those YVAAs is, and this is true for any of these York machines that run on their power, like their VSD modules, As those modules begin to fail, they do cause a lot of instability in the motor. That results in vibration in the motor because the electric field is unstable, which ends up leading to extra vibration stress. All right, so in that particular case, it could just be that the copper had a weak spot. It could have just had an issue and it ends up cracking. It depends on where it cracked. Like, I'd want to see like where it cracked, how it cracked. That would help me indicate, is it just kind of something that happened naturally over time, or did something else change? At the same time, I'd really want to pay attention to like listening to the compressor and feeling it. Is there abnormal vibration there? And are we dealing with a IGBT issue of some kind? Anyway, that's a very abbreviated answer to get that one. Teach me about dry bulb temperature, because this time is the humidity season. Please elaborate what the procedure is in the centrifugal chiller. Dry bulb temperature, and let's see, Jason was getting into this some too. Dry bulb is your sensible temp. It takes no moisture into play. Wet bulb is the latent that comes into play, so it brings in your relative humidity is involved with the wet bulb temperature or dew point compared to relative humidity. Relative to dew, so we were just describing wet bulb there. Okay, so as Jason stated, we can actually get. Okay, let me make some room here. Love all my new toys. They make this really fun. We're going to get more toys, by the way. They're just in progress. All right. So let's look at this as an example. All right. So this is our cooling tower connected to our chiller. Get some visual aids here. So discharge line coming down. This is our condenser. The water temperature between these two is going to be read in sensible temperature. That is a sensible heat getting passed between there. In terms of humidity, well, it's kind of water, so it's going to be a bit like 100% humidity between there and inside the pipe. But in terms of like actual temperature, that is what matters to us here, is what is the water temperature leaving this basin that we're feeding into this machine, and that's going to dictate what our compression ratio is, or our lift. Okay, so compression ratio, lift, all these terms are very interchangeable. We're just saying slightly different things, or we're saying it slightly different ways. That's a better way to explain that. Same thing, slightly different way. It is a different calculation, regardless. Sensible temp. The lower one, we have to stay below a certain temperature coming in. That's going to depend on a lot of variables. There's not a rule of thumb on this, okay? But if we get too high of a water temperature coming in, we will start causing issues in this centrifugal compressor. It will begin to surge, and it's not going to maintain the load properly. What dictates what temperature we can operate at will depend on what this tower can produce. So this tower is only capable of producing water temperature that is relative to the wet bulb. All right, so you specifically reference about dry bulb temperature, and then you bring in humidity and how this plays into a centrifugal. So the centrifugal cares about the sensible temperature of the water coming into it, but the tower, which is not deciding necessarily. It's not the way I want to say that. We can only achieve the water the tower is capable of producing, and the tower can only achieve the water based on the wet bulb temperature. Okay, So if you want to calculate your wet bulb temperature, you need the outdoor air temperature there at the tower, which you can do that with a psychrometer. I had mine sitting here a moment ago. It has ran away. Here it is. Okay, so we can use just the very basic. It doesn't have to be crazy accurate. All right, I really like this thing for just a basic psychrometer to have in my pocket. This is the Field Piece PRH2. There's a lot of people that find this thing to be trash. They don't like it. That's fine. I'm not changing your opinion. I'm just saying it has worked well for me. So I can use this to get my you can get your actual wet bulb temperature with this, okay? So you don't have to do a calculation. But if you don't have a psychrometer, but you do have, or if your psychrometer won't give you wet bulb, it only gives you dry bulb and relative humidity, with some of them, that's all they'll provide. I use a service or an app called, well, there's two that I actually use. This is my preferred, which is Psychrometric, okay? This app works really well. I can factor in. So basically, I just plug in my dry bulb and my relative humidity, and then I can spit out my wet bulb from there. Once I know what my wet bulb is, it is wet bulb, so WB minus, what would it be? I guess it'd be the other way around. Sorry about that. It would be I'm going to call it TA, tower approach, minus, no, it would be the other way, right? Would it? Oh, plus. That's my issue. Okay. I got to straight. I'm sorry. Wet bulb plus TA, which is tower approach, gives me my actual tower leaving water. Okay, tower leaving water temperature. So a tower approach, what that is the how close can we get to wet bulb. All right, it's same kind of approach that we would use for these heat exchangers. All right, so it's our saturation to leaving water temperature. That is your heat exchanger approach. All right, exact same concept here. We're just doing it with a cooling tower, comparing it to wet bulb. Most modern towers can do anywhere from 5 to 10 degrees Fahrenheit of approach when they're clean. Okay, when they're clean. The dirtier the tower gets, the poorer the condition the tower is in, the worse these numbers are going to look. They're going to get higher, just like we would have if we had dirty tubes in our heat exchanger on our chiller. All right, dirty tubes, higher approach value, not work so well. Same thing with this. Dirty tower, not function right, not work well. Simple as that. So once we know that, and these will have a design approach, okay? So the manufacturer, when they put the specs on this machine together, they will know that, okay, this machine is designed to manage this approach with all conditions being correct. So let's just say it was 10 degrees. So if we have a wet bulb of 75 plus a 10-degree approach with a clean tower, that means that the best that tower can possibly do is 85 degrees. That's the best it can do. Now, you may have situations where, and this may be true, especially if you're in a more desert, not rural, but a desert, drier environment, you may have higher wet bulbs during the day, but at night, you may see your wet bulbs drop significantly, especially during certain seasons. Okay, that's where when you see that wet bulb drop, well, so the number that is possible to be achieved drops with it. And that's where you may have a really high dry bulb. Okay, the dry bulb is not really important here. I don't care if I have 100 degrees Fahrenheit of dry bulb. All right, I don't care, because I can have a 65-degree wet bulb, for example, and with a clean tower, happily produce 75 degrees Fahrenheit of condenser water all day long, even if it's 100 degrees outside. As long as my wet bulb, which is my humidity, as long as the humidity is low enough, I can achieve those numbers all day long. I don't care about the dry bulb at that point, which is your sensible, okay? Your dry bulb is your sensible temperature. That's what a thermometer is going to read when you walk outside. That is dry bulb temperature. This is what is important here. And if we're not controlling this well, and we're not able to maintain a clean enough tower and work within the boundaries of lift for the machine, that's when we're going to start running into a lot of issues with surge and stuff. And so if you have low enough wet bulb temperatures, try your best to use them, utilize them. Let that tower get the condenser water down, which is going to lower your compression ratio or your lift, which is going to help you in so many ways. One, it's going to keep you out of surging, but two, it's going to it's going to make you far more efficient as a whole. Like, just your efficiency significantly increases by doing that. Now, if that, you're going to have situations to where you cannot get that water temperature down because you may be in an area that has extreme humidity. Okay. When that's true, you can only just do the best you can, but it's important. The staging on the equipment changes. Okay. So if we've got a scenario where this gets back into like a surge graph as an example. If we've got a scenario where we've got a high wet bulb, and let's say we've got 3 chillers. Okay, so CH1, CH2, and CH3. We have 3 centrifugals specifically. We have a high wet bulb, which means that we've got a condenser water of like 95 degrees Fahrenheit because of our high wet bulb. Well, in certain cases, it may make more sense to us. What we'd love to do is we would love to split the load on our facility between chiller 1 and chiller 2. Okay, so we want these two to be on together, but running at a part load condition. That's what a lot of logic would recommend. That don't run your equipment at maximum peak volume, because it's better to get them below that and let it kind of share between them and do a part load, which some machines function phenomenally well and efficiently at part load conditions. And we're also putting less wear and tear, all the things. Okay. So there is proper logic to this, and it is a very common thing to have happen. Or it's possible that either way, without getting too far into the specifics, we have 2 machines online, but technically we could have the load is in such a way to where we could force one machine to stage up really far and like close to maxing itself out, but it would mean really pushing that machine hard. Now, in our situation here, so we're standing in this plant right now. We're standing there. We have these 3 machines. We have a hot, really humid day. Both of these machines are occasionally surging. Both of them. At different points, not at the same time. We can't get our condenser water down any further, and the load is what the load is. So they're occasionally surging. We really don't want them to surge. We want to stop the surging. We're going to go look, and we realize that chiller 1 can handle the load if we allowed it to. So what we're going to do is we're actually just going to turn off chiller 2. And we're going to let all of that load feed into chiller 1. Now, we went from running at, say, 60%, 60%, on each of these before, to now, once we shut down chiller 2, this thing's running at 98% to maintain the load. Wide open. But guess what happened when we did this? Our surging stopped. We are no longer surging on this machine. We couldn't lower the condenser water any further. The temperature stayed the same, but our surging reduced. This is because of how the surge line will move with the load. So if we have a surge graph, okay, so this is going to be your lift. This is going to be flow. So lift is the difference between evaporator and condenser pressure, and then this is the flow is representing the total volume of refrigerant going through the compressor. So we have a line up here that is called our surge line. When we have, when we unload, we may, like in this particular case, we may have unloaded, and we're basically sitting right at this point. The machine at 60% was sitting right here, each of them, to where our lift could not be lowered, but we didn't have more load to get them above 60% with both of them online together. So at 60%, we're right there at that surge line, and that's why both of them are just fighting that surge line constantly, fighting. Whereas the moment we shut down chiller 2 and we increased the flow through that one machine, chiller 1, so the lift didn't change. Okay, so our evaporator saturation stayed roughly the same, maybe increased a tiny bit. So maybe the lift increases ever so slightly because we have a slightly higher condenser pressure and a slightly lower evaporator pressure. So, okay, I'm going to represent that right here. Lift increased. We are slightly higher from this point to this point. It won't be much. It'll be pretty damn close to the same. But what did increase is our flow between these two. So now we're over here at 98%. Now we're no longer on our surge line. So we could not change the lift. Our chilled water set point is the set point. Our condenser water is what it is. Fans wide open. We have a high humidity day. We can't change it. But we can change the flow by changing how we stage the machines. So by cutting back, or however this sequence looks, like we put more load on each machine. We made it work harder because it's either be more efficient or surge, which surging loses a lot of efficiency, by the way, a lot of efficiency. So whatever efficiency you think you're saving having two machines at part load, you're losing in whatever surging you're allowing to have happen. Whereas if you had no surging with one machine at a high load, you might be surprised what the efficiency calculations come out to be. Just saying. Anyway, we increased flow through the machine. We're moving more refrigerant through the compressor, but we didn't have to change our lift much to do so. And now that thing could run for days and never surge once. This is where we are limited by our condenser water, by what our wet bulb and our tower condition can do. But there are ways of strategically managing how we run the plant. And how we run the plant when we have lower wet bulbs and we can run a lower condenser water temperature versus high wet bulbs should change, should shift. It's not a one size fits all. I completely agree with the sentiment that it makes sense to just split the load between these two if our condenser water was down and we weren't pushing the surge line, because then we just lower the lift. The flow would stay the same, but we drop lift a little bit and we get off that surge line. But in the inverse, with high wet bulb, I can't do nothing about that lift. I can only do something about the flow. These are a lot of the fundamental basics that I cover in my certification course. Okay, I show you surge maps, surge graphs, and I talk through this very, very heavily, including from a staging standpoint. Okay, so this is just an overview to give you the concept here. Anyway, getting back to the original about just explaining dry bulb temperature and then having a high humidity season and how that is affecting a centrifugal chiller. Yep. Really good question. Okay. Good to see you, Jason. I'm glad you got to drop in. I will throw out there, and again, people have to come and go. So if you haven't heard me talk about it, I am going to start wearing more of the community shirts, hats, stuff like that. I'm going to repost the information here. I would love to be able to include your company in the process and being able to get to wear, like, represent, instead of just wearing the stuff I've been wearing, even my own hat. To me, it actually would be really fun to get to show and have the community more involved in that way, to where I'm wearing your stuff. Okay, this is a local contractor here in San Antonio to me, and this is a contractor, really close friends of mine. So are these guys, by the way, out of Colorado. All right, so I'm wanting to expand the library, and I want to represent the community as a whole more, and I want to represent better. And so in that context, I would love to get a shirt and a hat. Even if you are going to send a shirt, please just send me or if you're going to send anything, just send me a quick email. Let me know that it's coming. You can send it to that PO box that's in the comments. And I wear a 2XL. All right, so that my shirt size is 2XL. So if you do send me anything, I'd love to be able to wear it. So I need the right size to be able to put it on. Otherwise, you send me an extra large or something, I'm just gonna be, it's just a bit tight. Right? It doesn't fit so well. So anything smaller than an XL, I'm not even gonna get it on my body. It's not gonna work. Okay. I think we have time for another question. I saw one come in here. Yes, right here. Asking about the 19XR. Let's see. Yeah, we should have time. I'm going to actually get a chart pulled up for this. So if y'all would give me just a minute, I can get some fun graphics going. Right. Okay. All right. Let's come over here. Like I said, just give me just a second. I want to pull up. To me, this is a good one to actually show you Carrier's actual drawings, and we can kind of talk through them. I'll go back with this. Let's see. We're going to do both. Okay, we're going to start with just the refrigerant circuit, because you brought up oil cycle, flash tank, float chamber. Let's talk about, we'll go with a single stage, and then we will discuss a two-stage. All right, let me get the other version pulled up. So two-stage, nope, not that one. Right there. Okay, cool. We got both styles. Okay, let's start off with this one. So again, this is a 19XR. Let's start off with, or maybe we hit the question here. Could you cover some Carrier 19XR chiller stuff like oil cycle, flask, float chambers, etc.? So let's get into a single stage. So meaning we have a single stage compressor. There's only one impeller in here, and there is no second stage economizer. Now, when I say second stage, let me kind of explain this a bit here. What we've got is, this is our condenser. We can see we come through the suction elbow into the impeller, goes into the condenser. All right, we have condenser water flowing through the tubes, water-cooled system, centrifugal. From there, we have this inner chamber that Carrier refers to as the flask chamber. All right, this is basically a type of economizer. Now they refer to this, I think, as a flash subcooler, if memory serves. I think that's what flask is supposed to be short for, is like a flash subcooler. Essentially, it is a economizer in its own right. They just don't call it that. So what we have happening is the high pressure condenser gas comes in, gets condensed to a liquid, and that liquid collects here at the bottom. Well, on this chamber, there are a set of orifices. Those orifices flash that liquid refrigerant as it comes into the flask chamber. That makes this a medium pressure. So we went from high pressure liquid right here to a medium pressure liquid vapor mixture. Now what happens is the vapor ends up collecting at the top side of this chamber while the liquid drains into our metering device chamber. We'll get to that in just a minute. So we're going from high pressure to medium pressure saturated liquid vapor mixture. Vapor collects at the top, liquid collects down here. Now, part of what's happening here, and this is unique in the way that Carrier is doing this, they do actually have their condenser water flowing through that flask chamber. So most manufacturers that use a flash tank economizer, including Carrier, you'll see that in a minute, will actually have a line coming off, pulling that vapor back out of the economizer chamber. Carrier is not doing that. Carrier is actually then running part of their condenser water through that flask chamber to recondense some of that flash gas. Excuse me. So as that gas collects here at the top of the chamber, it does condense and it does drain down into the bottom and collect in our metering device chamber. Now this is where we get into the metering device itself. This is a float valve. So it quite literally floats based on the refrigerant level in this little chamber here in order to control the flow from the liquid flow from the condenser going to the evaporator. Again, this is a single stage system. There is a what they call a bubbler tube that comes off of the discharge side of the compressor and feeds to the bottom of the float valve chamber. And what that does is that's just constantly keeping a little bit of high pressure discharge gas bubbling up into this actual little float assembly. And that discharge gas allows that vapor that's trapped there is literally like a bowl upside down in your sink. You can simulate this. Okay, take a bowl, flip it upside down, put it underwater. You have a trapped vapor under liquid water. Okay, this is trapped discharge gas basically under this bowl, and that is going to float and fluctuate based on the liquid level in this chamber right here. I'll come back to this in a little bit to explain a little bit more. So as we leave this chamber, we have one line that feeds off into our cooling, so our oil cooling, motor cooling. The other primary line feeds down into our evaporator on the bottom side. This is a flooded style evaporator on these. And then so it enters into a distribution rail, and that goes up into the evaporator, boils off as it typically does, and then returns via the suction line. And these other lines are just part of the cooling circuit for the oil and motor cooling, returning back to the evaporator to reintroduce it and process down. So we have 3 pressure states in this machine. We have 3. We have our high pressure, our medium pressure, and then our low pressure. Okay, 3 pressure states. And you can actually kind of see that here. So we have refrigerant liquid, refrigerant vapor, refrigerant liquid vapor via these here. All right, so you can see the distinctions that they're trying to kind of make via this chart. Yeah, that's the basic kind of flow and process on this. Now, if we come over to a 2-stage machine, then we introduce a more traditional version of a flash tank economizer. Everything we've just discussed stays true. Okay? We still have the same type of condenser. We still have the same type of flash tank. We still have the same type of float valve assembly for the feeding the economizer. We also have another float valve in the economizer. Okay, Carrier has functioned fairly well using these float valves. Other manufacturers have radically different ways, usually using some kind of liquid level sensor to control this process, but Carrier has opted for these float valve assemblies. Now, something I want to explain with the float valve while we're here. This does actually naturally track with the load on the machine, because part of what we think about is, hey, load is increasing, and so my flow to my evaporator, refrigerant flow, would also need to increase as well. If we come back over here, we can maybe simplify this a bit. So I'm increasing my flow through the compressor by drawing more on the evaporator. But what's also happening is this liquid level in this machine is also going to fluctuate based on load. The more load we have, the more volume we're pushing into the condenser, the more we're going to actually raise that refrigerant's level a bit. As that level increases, it naturally allows the metering valve, the float valve, to open further. Okay, so we're opening further in order to flow more refrigerant to the evaporator so we don't starve it, all right? So it becomes this very natural process where this float valve automatically adjusts, because it's not an EXV. It doesn't have an electronic adjustment. It is fully mechanical, but unlike a TXV, right? A TXV has a sensing bulb. This doesn't have any of that. This is fully fluctuating based on the amount of liquid refrigerant stacked in here. So as load increases, this liquid level increases, valve opens more, flow is increased as a total, feeding into our evaporator, and the process balances itself really, really well. This is also true on this 2-stage with a secondary economizer. So that's why when I reference this, Carrier does call this their economizer. They call this their flash chamber, and it's fair enough, okay? I don't knock Carrier for not calling this an economizer, because in the most technical engineering sense of the word, it's not the same kind of economizer as this is, but in almost every facet, in my opinion, as a technician, which is where I'm coming at this from. I am not an engineer. I am a technician, though. So, as a technician, it is fair, in my opinion, to reference this as an economizer. So, this would be, and they're not the only people to use a two-step process. Train does the same thing. They have a first stage economizer and a second stage economizer on their CTV series. Okay, so you can, the same kind of thought process you would have on one of those machines is the same thing here, where we have a first stage metering device feeding into our economizer that leads through a second stage metering device feeding into a second stage economizer. Then we have a third stage metering device going to our evaporator. Okay, we're just doing this same process in multiple steps. Now, in this particular case, we have the same style of float valve in here, but then we have this proper flash tank economizer where we have a line that draws the flash gas off of the economizer back into the second stage port on the compressor itself, the economizer port. So that's interjecting a medium pressure gas in between the two impellers. Okay, to have this economizer, we have to have a two-stage at minimum compressor. Otherwise, these styles don't work. At least specifically in centrifugal world. There's other ways to do it with a screw and a scroll, but with centrifugals, that means two impellers at minimum. The more impellers we have, the more interstages we have, the more we can break this process down, which Train does utilize. Anyway, getting back to Carrier. So we come in as a medium pressure mixture, leaving this metering device. We feed into this economizer. The flashing that happens from this metering device, that gas draws off, and basically we're just utilizing a pressure enthalpy chart in order to maximize refrigerant effectiveness. Don't get overwhelmed with the terms or the words that I'm saying, please. And I talk about this stuff at length in my course. That's why it exists. I keep bringing it up because it's why I made that, to explain these things properly. Today, just if you're not familiar with these terms, it is okay. Write them down, reference them later, whatever you need to do. So the vapor draws off back to the compressor. That increases the effectiveness of the liquid left behind. Same exact thing we're doing up here. The liquid that sits in here is more effective refrigerant-wise than the liquid sitting in here. All right, so the high pressure liquid in the condenser is less effective than the medium pressure liquid sitting in the inside of the flask chamber. In terms of, like, if we were to chart where these two liquid refrigerants are on a pH chart, more effective. Same thing when we get to this economizer. The liquid sitting here is more effective than these other two. Once we draw the vapor off specifically, then we feed into our evaporator. So we have another float valve that it's not the same setup. So this one is using an actual float ball. I'm sorry, this one is actually using the bell-shaped chamber with a bubbler tube. This other style has an actual ball armature that will open and close in order to adjust a flap, if you will, to control flow out of the economizer down into the evaporator, which then feeds into a distribution rail assembly, which then continues the cycle back to the compressor. Okay, and then we also have the motor cooling and oil cooling lines coming down just the same. None of that changes. That's our basic process here. Let's see. Anything else I need to hit on? Yeah. That's your flask and float chambers or float valves, as Kerry refers to it, inside of a 19XR centrifugal. There obviously, as there always is, there's more we could get into if we needed to. I don't have time to get into the oil circuit now, but that is something that I can come back to next time, as I can get the oil circuit drawings pulled up and we can talk through what is the oil cycle for a 19XR. So I can save that for next time. I also see the multi-stack question there. I will save that into our on my backlog list, so I keep everything that I haven't got to answer yet. It all stays there just to make sure I keep track of it and I can get to it as I can. That being said, I really appreciate everybody's time. Be safe, be careful out there, enjoy your week. I'll see you guys later. MTT. Make the time for your family, for your spouse, and for your kids. They really need you.